This is lesson 2.7, solve absolute value inequalities. The learning objectives are to solve absolute value equations, solve absolute value inequalities with less than symbols, solve absolute value inequalities with greater than symbols, and solve applications with absolute values. All right, so let's start with solving absolute value equations before we get to the inequalities. We'll define what an absolute value is. The absolute value of a number is its distance from zero on the number line. The absolute value of a number n is written as the absolute value of n. So these vertical bars around n are the absolute value symbol. And the absolute value of n is greater than or equal to zero for all numbers. Let's state that again in an everyday quote. Absolute values are always greater than or equal to zero. So I'll describe this on a number line. Here's a number line with 0 on it. Now, if I want to state the distance, find the distance from this negative value of -3 to 0, well, that distance, okay, measuring it, is a distance of 3 units. So absolute values tell me that distance. If I take the absolute value of -3, the result is +3, because it's the distance that I'm measuring from that number to 0 on a number line. Let's take a positive value. Like, I'm going to take 5. Okay, what is the distance from 0 to 5 on the number line? Well, that distance is 5 units. Okay, so it would make sense that if I took the absolute value of 5, it equals 5. Now, the absolute value of a negative number is positive, and the absolute value of a positive number is still positive. That's why we're saying absolute values are always greater than or equal to 0. It's impossible for an absolute value to be negative because a distance can't be negative. All right, so I have now described an absolute value to you, and now let's talk about absolute value equations. For any algebraic expression u, and any positive real number a, if the absolute value of u equals a, then u equals -a or u equals a. The idea here is that, if the absolute value of u equals a, then u, the thing in the absolute value, could have equaled +a or it could have equaled -a. That's what we're saying here. Now, that is a rule that we're going to use for absolute value equations. When we are solving absolute value equations and absolute value inequalities, the objective is to drop the absolute value symbols and proceed. I'm going to train you on how you can drop the absolute value symbols to solve. Great. So example 2.68 says solve these 3 equations. The first one says the absolute value of x equals 8. Well, what could the values of x be that cause this to be true? All right, so what could x equal? Well, it could equal -8 or it could equal +8. Let's think about that. So if I plug -8 in here, the absolute value of -8 is +8. And if I plug +8 in for x, the absolute value of +8 is +8. So these are the 2 solutions to this equation, right? Starting nice and easy. Let's look at the second example. This says that the absolute value of y is equal to -6. Now, there should be big alarms going off in your head when you see an absolute value equal to a negative number, because absolute values are always greater than or equal to 0. And -6 is not greater than or equal to 0. Therefore, there is no solution to this absolute value equation. I challenge you to always analyze the absolute value and realize that if you have an absolute value all by itself and it's equal to a negative number, then there must be no solution to that equation. Okay, now a third version that you may encounter is this one, which says the absolute value of z equals 0. And so what are the possible values that z could be? Well, z could equal 0 itself. there is only one number, um, in this case, because 0 is neither positive nor negative. And so, in this first case, right, we had the absolute value of a variable equals 8. And so I had two solutions, -8 and +8. This will always be the case if this value is positive. Now, in this case, the absolute value of y was -6, and I notice, hey, that is a negative. That's not even possible, so there's no solution to that. And then the absolute value of this variable is equal to 0. That's neither positive nor negative, so there's only one solution, and that's 0. Great. Well, we can increase the complexity of absolute value equations by having other operations inside and outside of the absolute values. So here's a quick 4-step process of how to solve an absolute value equation when you've got some algebra to do. Step 1, isolate the absolute value expression. Step 2, write the equivalent equations. Step 3, solve each equation. And step 4, check each solution. So let's go through it step by step. Now, for example 2.69, we have to solve this equation that says the absolute value of 5x minus 4 minus 3 equals 8. First, isolate the absolute value expression, getting it all by itself. And so I see this minus 3 outside of the absolute value. I'm going to add it to the other side of the equation to isolate the absolute value. I rewrite the absolute value of 5x minus 4, and I know that it now equals 8 plus 3, which is 11. Okay, so these absolute value symbols that we have right here on either side, our goal is to drop them so that we can finish solving the equation. But to drop the absolute value symbols, we need to set this stuff inside of it equal to positive 11 and then set it equal to negative 11. All right? So we know this stuff in here could represent negative 11 or positive 11. So here we go. I take 5x minus 4 and I set it equal to negative 11. And I also take 5x minus 4 and I set it equal to positive 11, creating two separate equations. Now I'm going to solve both of these equations and find two solutions for x. Here I go. I add 4 from left to right. And I'll do it in both cases. I'll solve both equations simultaneously. And I get 5x equals negative 7 in this case, and 5x equals 15 in this case. Now I divide by 5 in both equations. And I get x equals, well, dividing by 5, yeah, x equals negative 7/5. That's my first answer. And then x equals 3, because 15 divided by 5 is 3. That's my second answer. And so the solution to this absolute value equation that we started with is negative 7/5 and 3. I'll separate my answers with commas and reporting my final answer. There you go. Let's try some more to practice this. Okay, so here's example 2.70. I'm going to talk you through the same process. All right. Now, the goal, step 1, is to isolate the absolute value. So here's my absolute value. It's the absolute value of x minus 6. All of the other things like this plus 5 and this multiplication of 2, I'm going to use algebra to move them to the other side of the equation. So, first step, I would subtract 5. Do the easy stuff first, right? You can't proceed until you do that easy stuff. And so I get 2 times the absolute value of x minus 7. And then that equals 9 minus 5, which is 4. Now at this point, I'm going to get rid of the 2 that's right here because I haven't isolated the absolute value all the way. I now need to divide 2 to isolate the absolute value. So I do that. And I get an equation that says the absolute value of x minus 7 is equal to 2. 4 divided by 2 is 2. Great. Now, take the absolute value stuff, right? Inside the absolute value, we have x minus 7. And we're going to create two equations to drop the absolute value symbols. We're going to say x minus 7 equals negative 2, and x minus 7 equals 2. Okay, two separate equations. X minus 7 equals negative 2, and x minus 7 equals 2. These are the possible solutions. I'm now going to solve these equations for x. So I add 7. I'm solving both equations simultaneously since they have the same operations. I get x equals negative 2 plus 7, which is 5, and x equals 2 plus 7, which is 9. These are my two solutions. I'll report my answer, separating my solutions with a comma. Great. Let's look at example 2.71. Here I see the absolute value of 3 halves x minus 4 plus 11 equals 3. Okay, so my objective is to get the absolute value by itself first. And so I use algebra subtracting 11 to the other side because 11 is not inside the absolute value. Now I have the absolute value by itself. I'm going to write this really nicely. The absolute value of 3 halves times x minus 4 equals 3 minus 11, which is negative 8. And now there should be big alarms going off in your head because we're saying that the absolute value of something equals a negative number, which cannot happen, right? Ding, ding, ding. Absolute values are always greater than or equal to 0. And so if you encounter this moment, right, when you're doing an assignment or something like that, you're going to stop right here and you will not proceed. You're going to say there's no solution. Okay. So if the absolute value all by itself equals a negative number, then you stop and you don't try to solve anymore because there is no solution to that absolute value equation. Cool. Let's move forward. And now sometimes in absolute value equations, we don't just have like an absolute value on one side of the equation, we have an absolute value on both sides of the equation. Okay, so the absolute value of 5x minus 1 equals the absolute value of 2x plus 3. So how do you handle that? Well, here's a little info for you. For any algebraic expressions u and v, if the absolute value of u equals the absolute value of v, then u equals negative v or u equals v. It's kind of the same setup. And our goal is to drop the absolute value symbols so that we can proceed to solve. Okay? So here's what you're going to do. You're going to take, this stuff right here, and you're going to set it equal to the positive version and the negative version of this separately in two separate equations. I'll set it up for you so you see it. I have 5x minus 1 is equal to, well, 2x plus 3. I can just use the original stuff. And I can also write 5x minus 1 is equal to negative of 2x plus 3. This is how you set up your two equations, all right? Make sure that you take the absolute value here when you apply the negative version of it. Just wrap this in parentheses, and you'll have to distribute this negative sign into both the terms of that piece. Great. Now, each one of these equations, I'm going to solve for the variable x. Now, you'll see that I have the variable x on both sides of the equation. So here I'll subtract 2x from right to left so that all my terms with x are together. And I'll add the constant 1 from left to right. Okay, so this stuff cancels, and I'm left with 5x minus 2x, which is 3x, is equal to 3 plus 1, which is 4. And now I divide by 3, and I find out, oh yeah, x, it equals 4/3. That's my first solution, solving that first equation. Okay, moving on to the second equation that I set up. This is rewriting it, 5x minus 1 equals negative 2x minus 3, because I've distributed this negative into both of the terms, and so I've got this. Now, moving my terms with x in them to one side and my constant terms to the other side, I can now rewrite this. This stuff canceled, this stuff canceled. 5x plus 2x is 7x, and that equals negative 3 plus 1, which is 2. Now I'll divide 7, and I know that x equals 2/7. Great. I have found two solutions, and I'll report them, separating them with a comma, right? So I'll say x equals 4/3, comma, 2/7. These are the two solutions, and they're both fractions, and it feels good to find fractional answers as opposed to integer answers, because integer answers start getting boring after a while. Great. Hey, now that we have solved absolute value equations, we're now going to change our objective to solving absolute value inequalities. And we have two versions. So we have absolute value inequalities that use less than or equal to symbols. And we also have absolute value inequalities that have greater than or equal to symbols. And so I'm going to train you on how to handle both situations, but I'll do it one at a time. Great. So how do you solve absolute value inequalities with less than or equal to symbols? Step 1, isolate the absolute value expression. Step 2, write the equivalent compound inequality. Now here's how you do it. So it's the same whether you have less than or equal to. If you see the absolute value of u is less than a, you're going to rewrite it as negative a is less than u, which is less than a. So you're rewriting it as a compound inequality. Now, it's exactly the same if you have a less than or equal to symbol. Just make these less than or equal to symbols, and you're good to go. Great. It'll all make more sense as I do some examples. But once you've done that, step 3 is to solve the compound inequality. Step 4 is to graph the solution. And step 5 is to write the solution in interval notation. Since we're dealing with inequalities, our solutions aren't a single answer, they're intervals of answers. Great. So let's go ahead and dive into this. Example 2.73, solve the absolute value of x is less than 7. Graph the solution and write it in interval notation. So looking at this and comparing it with our step process, I'm going to write it above, and I'm going to say the absolute value of x is less than 7. All right, where this u has been turned into x and this a is 7. So when I rewrite it in its equivalent form on the right, I'm going to take 7 and make it negative. And I'll say that that's less than x, which is less than 7. Okay? So I'm taking this value and I'm making it the negative version and putting it on the left. And then I keep that positive 7 on the right-hand side. They're my lower bounds and my upper bounds of my compound inequality with the variable x in between it. And I'm done. All right, so I have solved it. I can say, the absolute value of x is less than 7 is rewritten to negative 7 is less than x, which is less than positive 7. Now, how would that look if I graphed it on a number line? Well, my lower bound is negative 7, and my upper bound is positive 7, and x is everything between them, but I have open dots, right? Open dot at negative 7, because it's less than, not less than or equal to. Open dot at 7, and I'm shading the entire region between. Great. Now I'm going to report my solution in interval notation. So in interval notation, I put a parenthesis because I've got an open dot at negative 7. And then I end the interval at 7 with a parenthesis because another open dot. So open dots, when I write interval notation from a graph, are parentheses. Okay? Okay, I'm just showing you very clearly. Less than symbol, open dot. Less than symbol, another open dot. Open dots, well, they are parentheses in interval notation. This is my final solution, and I am done. Okay, so that was a nice easy version. Let me go ahead and show you the same idea, maybe a little bit more complexity, okay? So here I go. Example 2.74, solve the absolute value of 5x minus 6 is less than or equal to 4. Graph the solution in interval notation. So maybe I do a comparison and I hope you guys see this. So I have the absolute value of 5x minus 6 is less than or equal to 4. So this u is the stuff inside the absolute value, which in my case is 5x minus 6, and this a right here is 4. So I'm going to rewrite this in its equivalent form like this. Okay, so I take this 4 and I make it negative, and I write it here. So I've got negative 4 is less than or equal to u. That's the stuff inside the absolute value. For me, it's 5x minus 6, which is less than or equal to 4. I have written this statement in its equivalent form here as a compound inequality. All right, so I get to this point and I write my answer. I say, well, this is negative 4, which is less than or equal to 5x minus 6, which is less than or equal to 4. But this inequality, this compound inequality, is not solved for x. I don't have x all by itself. And so I'm going to solve it like we've discussed, solving a double inequality in the last lesson. I'm going to add 6 to all 3 sections here. Okay? Now, negative 4 plus 6, that is 2. And so I can say 2 is less than or equal to 5x, which is less than or equal to 4 plus 6, which is 10. Okay, now I need to divide 5 in all 3 sections of this double inequality. There you go, and I have now gotten x alone. So rewriting it, I have 2/5 is less than or equal to x, which is less than or equal to 2, right? 2/5 is less than or equal to x, because the 5's cancel, which is less than or equal to 10 divided by 5, which is 2. If I write this on a number line, then I take the smaller value and put it on the left, that's 2/5, and the larger value and I put it on the right, that's 2. And showing you this, you know, we were talking about less than or equal to symbols, right? Because this original statement had a less than or equal to symbol, our compound inequality has less than or equal to symbols here and here, and that's why I'm going to put a closed dot at these locations. So I have a closed dot that I place, and x is between them, so I shade the region between these two values. What is the interval notation for this? Well, closed dots are brackets, so I put a bracket to start my interval at 2/5. And then my interval continues all the way until 2, and I put a bracket at 2 because that was a closed dot as well, right? So less than or equal to symbols produce closed dots, which are brackets in interval notation. And this is my final answer that I will report. Done. So we just looked at 2 examples on how we solve absolute value inequalities with less than or equal to symbols. So the question naturally comes up, how are things different when we solve absolute value inequalities with greater than or equal to symbols? And here's the step process. It's exactly the same except for how we set up the compound inequality. Well, step 1, isolate the absolute value expression. Step 2, write the equivalent compound inequality. And so if I see the absolute value of u is greater than a, I will rewrite it as u is less than negative a or u is greater than a. If I see the absolute value of u is greater than or equal to a, I rewrite it as u is less than or equal to negative a or u is greater than or equal to a. These are the same thing, but instead of greater than symbols like that I had here, I have a greater than or equal to symbol here. And so that changes this symbol to a less than or equal to symbol and this symbol to a less than, greater than or equal to symbol. Now, step 3, solve the compound inequality that results. Step 4, graph the solution. Step 5, write the solution using interval notation. Let's show you some examples. And so when I see this example 2.75, solve the absolute value of x is greater than 4. I will immediately compare this with this original statement right here, right? So I'll write it up above so you see it really clearly. I have the absolute value of x is greater than 4. And so let's practice rewriting it in its equivalent form. All right, so I will say, to drop the absolute values, I'll say x is less than negative 4, or x is greater than 4. All right. So we're converting this to this. And this is an easy example because after the conversion, we don't have any more algebra to do. So my answer is x is less than negative 4 or x is greater than 4. This or word is really important. We talked about it in our last lesson. When I graph the solution of this, I go to the values of negative 4 and positive 4 on the number line. And I put open dots at their location. Why am I putting open dots? Well, because this says x is less than negative 4, so that less than symbol means I have an open dot. And x is greater than 4, that is a greater than symbol, open dot. Now, if x is less than negative 4, I shade everything to the left of negative 4. And if x is greater than 4, I shade everything to the right of positive 4, like this. This is my solution graphically. But I'm going to write the solution in interval notation. And you'll notice this solution has two shaded regions separated from each other. Okay, we always write interval notation from the left side to the right side. We scan the number line from left, starting on left, to right. Okay, so writing interval notation, I would write negative infinity, comma, 4 parentheses. Okay, this interval represents this shaded region. And I would write 4 comma infinity because that interval represents this shaded region. And to finish off, I would put a union symbol between the two intervals. The union symbol connects two separated intervals together. This separate interval is now connected with this one, and that's my interval notation. Great. Well, let's increase the complexity just a little bit, for example 2.76, to see how we would handle this scenario. All right, so this is a greater than or equal to situation, so I'll follow the format for the greater than or equal to situation here. And I'll write this stuff up above here so you can see a comparison. I have the absolute value of 2x minus 3 is greater than or equal to 5. So how would I rewrite that stuff, getting rid of the absolute value symbols? This is the format, okay? So I take the stuff that's u, in this case 2x minus 3, and I set it less than or equal to negative a, which is negative 5, okay? So my first inequality I write is 2x minus 3 is less than or equal to negative 5. And then I take the stuff that's u, which is 2x minus 3, and I set it greater than or equal to a, which is 5. Okay, so I have 2x minus 3 is greater than or equal to 5. These are the two pieces. Okay, so I'll rewrite them down here. I have 2x minus 3 is less than or equal to negative 5, and 2x minus 3 is greater than or equal to 5. I will solve both inequalities. Right? And I have the word or between them, by the way. Great. So let's solve both inequalities. I'll do it kind of faster here. So I'm going to take 3, I'll add it from left to right, and I'll do it simultaneously for both inequalities. Cool. So I have 2x is less than or equal to negative 5 plus 3, which is negative 2 in the first case, and then 2x is greater than or equal to 5 plus 3, which is 8 in the second case. Now I'm going to divide by 2 from left to right in both cases simultaneously. And now I find out my first inequality is x is less than or equal to negative 1. Okay? And then I also figure out that, well, x is greater than or equal to 4 in the second case. Okay? So I have a statement that says x is less than or equal to negative 1 or x is greater than or equal to 4. So let's hop on our number line to visualize this graphically, the solution. Now, the smaller number is negative 1. I put it on the left. The larger number is positive 4. I put it on the right of the number line because, smaller numbers are further left on the number line than larger numbers. That's why I'm doing it. Now, I think, well, what type of dots should I use? Open dots or closed dots? And for negative 1, I use a closed dot. And for 4, I use a closed dot. Why did I do that? Because I had less than or equal to and greater than or equal to symbols. Yeah, those have closed dots. Now, if x is less than or equal to negative 1, I shade all of the region to the left of negative 1. And if x is greater than or equal to 4, I shade all the region to the right of 4. This is my solution. And I'm going to write the solution, instead of graphically, write it in interval notation for my final answer. And so I notice that there are 2 shaded regions that are separate from each other in space. And so I'm going to write the first interval from negative infinity until negative 1. And I use a bracket at negative 1 because it's a closed dot. Closed dots have brackets, right? And now I write the second interval, which starts at 4 with a bracket, and it goes on to infinity. There it is. And then I connect the 2 intervals with a union symbol, showing that these 2 pieces have been combined together to make my interval. All right, remember, interval notation is always written from left to right. So we start on the left side, which is negative infinity in this case, and we go until negative 1, and we write a bracket, okay, because it's a closed dot. Then we have a union symbol because there's like space in between. Now I start my interval again at 4 with a bracket because it's a closed dot, and I go off to infinity. Now infinities never have brackets with them. They always have parentheses. Little reminder. And now that you know how to solve absolute value equations, absolute value inequalities with less than or equal to symbols, absolute value inequalities with greater than or equal to symbols, I'm going to leave you with one last example today in which we will apply this knowledge to the real world. Great. So here's example 2.77. The ideal diameter of a rod needed for a machine is 60 millimeters. The actual diameter can vary from ideal diameter by 0.075 millimeters. That's like it's a tolerance, okay? There's a tolerance of 0.075 millimeters for the production of this rod, okay? What range of diameters will be acceptable to the customer without causing the rod to be rejected, okay? Now, to be rejected, it would have to be outside of the bounds of this plus or minus this, okay? But we can use an absolute value to represent this, in which I would set up an absolute value as the absolute value of x minus 60 has to be less than or equal to 0.075. All right? So if I take the absolute value of the rod in question, minusing off 60, which is the ideal diameter of the rod, it has to have a tolerance that is less than or equal to 0.075. And if it's greater than 0.075, it will be rejected. Okay, so this is the setup. Now, this is a absolute value inequality with a less than or equal to symbol. And so looking back, how did we handle those? We handled a less than or equal to symbol with an absolute value this way. So we're rewriting this in this format right here. Okay? So it'll make sense that I'm taking this 0.075 and I'm making it negative as the lower bound of my inequality. Okay, negative 0.75. And I'm saying that it's less than or equal to x minus 60, which is less than or equal to positive 0.075. Let me fix this up. There you go. All right, so we just created a double inequality, and now we're going to solve it for x, right? The diameter of the rod, the actual diameter of this rod. So to do it, we can add 60 in all three sections of this double inequality. And we can say, hey, negative 0.075 plus 60 is 59.925. Just little calculator right there. And that's less than or equal to x, which is less than or equal to 60.075. Okay? So this is the solution. I have now solved for x, okay, which is the diameter of the rod, and it's got to be between this lower bound and this upper bound for tolerance so that it's not rejected. Okay, because we need to produce something for the customer that's within that tolerance. And that's how it's done. So this is an example of using an absolute value inequality to solve for something specific in the industry. Okay, well, there you go. We have now discussed all things absolute values, equations, and inequalities. And we're going to go ahead and use this a couple more times in the near future, this knowledge about absolute values. Great. Thank you. Have a wonderful day.